Hi, good morning.
Hi, Yuri. How are you?
Great. Well, it is 8 in the morning here, so
Whoa.
yes, not exactly my time, but well, it's
Yeah, it's about lunchtime here.
yeah.
Yes.
Usually it's the time well I wake up by lunchtime. Yes, so
That's right.
yeah. So let me see
Hello.
the,
Hello.
hi.
I think someone is here.
Hello. Yeah.
Hello.
So Purushottam will introduce you
Good.
Well,
in the session. I think you
so
go. Yeah.
so there is someone who introduces the chairman. Yes, and then the
Yes.
chairman introduces the others. So it's a
Yes. The chairman is the boss of
complicated
the session.
hierarchies you have. Yes, so
Purushottam keeps saying that. It's too many
usually,
introductions.
yes. Usually, when I chair a live conference meeting, I appoint a deputy chair.
Okay.
Yes, yes. It is a person. It is a person who is doing like this to me when I fall asleep.
In
Here,
online mode.
unfortunately, yes, I cannot, but I'll
Is it?
try. I'll try to keep well. So.
Ayanu, he is ready. Have
Okay.
you finished your lunch? Not yet.
No, I'm going to have right after the lecture begins.
Yeah. Let me find the. I need okay. See
I
the
will switch it.
speakers. Uh,
Media, please do not record these informations now.
No,
If there is some.
the recording is paused. I mean,
No,
paused.
from our side.
Yeah, on the
Media should
right.
not be live streaming it.
Yes.
They do it on their own. They don't need us. You know that, right?
Yes.
yeah. So today,
Yes.
yes.
Your
So
lecture series is also announced for Spark.
Yeah, that's right.
yeah, I saw it. Yes. Yeah. I only asked Rashid to do some little correction on the website,
Okay.
and then I will
Okay.
show it to people. So today is Luca, Chakraborty, and Waldschmidt. Yes?
Yes, that's right.
Okay, very well.
Okay. Onu can do it. Then Purushottam does not need to do it. You introduce Yuri. I cannot hear you. You're muted.
Oh,
Well,
oh
I
yes.
think it's
No, please.
it,
No, I think Raj sir should
Florian
do
is
it.
here. Florian is here.
Florian is here.
Hey, good morning.
Hi, morning.
You are awake?
So you see, there is yes, but I have to be. Yes. I will
What
be
you...
the chairman, so be
Oh, I
you
see.
have
That's
to
why. That
be.
explains the mystery.
Yes, don't explain, don't mess with me. You see,
Or maybe I thought you were in India or something. That's
yes,
why
and
you are awake.
you see, the point is, no, unfortunately, I'm not in India, but well, what we have. Point is that, well, I already told the people, usually when I'm chairman, I appoint a deputy chairman.
Oh, I see.
But here I cannot do it. Well, I can appoint, but it will be useless.
Can we make some try with my slides, see if they work?
Yes, sure.
All right.
I should make you co-host. Yes, they already did.
Yeah.
Yes. So you.
Okay,
Yes.
so here's my
Very well.
slide.
Yes, very well.
Let me see if I can make it full screen with it, because sometimes when I make it full screen, it doesn't change. Do you see that
Now
it's changing?
it's already quite enough.
Is it
It's
changing?
already quite enough.
It's not changing.
No, it hasn't changed, but it is big enough.
It's
Wait. I have to do something.
yeah, it's even bigger. Yes, now it's bigger.
Now it's
But
bigger.
now it is cut from the side, so better like before.
Oh.
No, this is not good. Now we see it cut. It is cut on the left. Now it's okay.
Now it's okay.
Yeah. You can also make Control L.
Is it changing now?
It's changing, but not significantly. But you can make Control L. Try to make Control L and see what it is. Or what is this program? This is not what this program is.
So I'm changing my slides on my side. Do you see that?
No.
Okay. So let's go
I
to
just
the
see your title page.
Okay.
No, now it's not good. And not good now. It's cut. Yeah, now it's okay.
Now it's okay.
Now it's okay, yes.
Okay. And you can see that it's
50,
changing.
yes, okay, yeah, it works. 50 slides, okay, great, yeah.
I have 50 minutes, yes.
50 minutes. But you are going to run them very quickly.
Yes.
I had 22 slides.
Oh, I see. Very good.
But my slides were very charged, so maybe I had
see. Yeah, my slides are not so charged.
with on every slide. So
well, I tend to put many slides to explain it to myself, just to make sure that I understand it.
yes, it's the most important thing in your talk that you understand it yourself.
Yes.
So otherwise.
So how is Bordeaux?
Oh, sunny, good.
Oh, I miss those places because here in Germany it's
You
cloudy.
will be soon here, yeah.
True, in about a month.
Yeah.
When am I due there? 20 or something?
I don't remember. You
Yeah,
said
I think it's around the middle of April.
yes, middle of April. Yeah.
Yes,
So,
that's what I'm saying, in 1 month.
actually, restaurants are closed now, and
I might be thinking about moving it by 1 month. Do you think it will be possible?
what?
I might be thinking about moving it for 1 month, so to come in May instead of in April. Do you think that would be possible?
They might be possible, but you need a new document to do
Oh,
it.
you mean this form needs to be signed again?
Yes.
Okay. Because I was hoping to be in May and June in Bonn and back to Saarbrücken in July.
Mhm.
But then it turned out that in Bonn, they only invited me for 1 month, for June, and then I'll be back in Saarbrücken in July. So now it looks a bit silly that I come to Bordeaux for 2.5 weeks, then I go back to South Africa, and then I come again to Europe.
Okay, don't tell to anybody that you go back to South Africa.
Okay, yeah, I'm just telling that in Zoom to everybody who is present.
Okay, we'll discuss it later, not now. Okay.
Sure.
Hi, Florian.
Hi, good morning or good day. How are you?
We are fine. And what is the time for you?
Oh, I'm in Germany here, so it's
Okay.
8 something, 8:20.
Yeah,
So it's morning for you, for both of us.
Yeah.
you're in Germany now. Yes. Yeah.
Yes, I am in Germany. In South Africa, it would be by 1 hour later, but that will change at the end of the month.
Yeah.
At the end of the month, Europe will change time. So,
But how is the weather in Germany or in France?
well, it's been rainy. It's not so cold anymore. It's been a bit cold in January.
Okay.
Then February, beginning of March got a bit better. All right. There's nothing to do here. Everything is closed anyway.
And what about the vaccine process? Are you getting it here? Can you?
I don't know.
No, they stopped it.
I don't know what's happening in Europe. I heard in Italy
some
they do
problem.
it.
They stopped it?
They found some problem in the main vaccine that they use, and they stopped it in the whole Europe.
It's the
Oh, wow.
AstraZeneca vaccine.
there
They've
is-
stopped it for some reason. Some
Yeah,
complications with this vaccine.
there are some
Blood-
complications. One person is in 100,000 develops some serious complications.
Oh, wow.
Yes, but you see, it's
But
enough.
it's one person in 100,000 is better
Yes,
than
yes, but you see,
the
people
virus itself. You see.
I'm just
people
getting
do
it
not
over
understand big digits. You see, for people, 1 in 100,000 and 1 in 100 is the same. And you should explain it to people. See.
I think the only country that has good vaccination program maybe is the United States and Israel. I think the rest
Israel,
are
UK.
slow.
I believe that in UK they
Oh, I see.
doing well. Yeah.
Okay, I'll be right back.
Yuri Bilu. Yuri,
Yes, I'm here.
hi, how are you?
Great.
Hi, Florian. No,
Florian left for a while.
okay.
He will be back. Don't worry. We will not start the talk without him. So.
Hi, Florian.
Hey, how are you doing?
I'm okay.
Hi,
What about you?
I'm okay. I'm okay.
So, how is your family?
My family is good. My daughter is a university student already.
Very good. Very good.
Oh.
Nice. Nice hearing from you.
Very
Good.
nice. How is the COVID situation in your place?
Hey, Balu. Happy
Yes, sir.
birthday. How are you doing?
Thank
COVID
you.
Situation here. I'm in Germany now,
Oh.
but I'm in a small place in Germany, so we don't feel anything, but everything is closed.
Oh God.
But we live in the middle of a forest, so I can walk through the forest and go to my house and come back to work. And there's about 3 or 4 people that come to this building. Everybody else stays home.
Oh.
And you don't meet any viruses when you walk in the forest.
No, not any viruses. If we walk around the corridor here, we are supposed to wear a mask if we are in the university building. And once we were told that somebody tested positive for COVID and that person has met a different person and they played tennis together,
Oh God.
but none of them actually came to the building. But because of that, we were not allowed to come for 10 days.
Oh.
So they are very careful.
Okay, so good morning, good afternoon, good evening, everybody, wherever you are. So welcome to the penultimate day of the conference. I will hand over the session to Yuri, who will be taking care of the next 3 lectures. Yuri, you are the master and commander.
Yeah. Okay. Thank you. So good morning, everybody. We are now starting today's morning session. So our first speaker is Florian Luca, well, from the University of Witwatersrand in Johannesburg, currently in Saarbrücken, and he will speak on a transcendence criterion. So I think we still have maybe 2 minutes.
Yeah, we have to.
Yes,
Let
we
us
still
wait.
have 2 minutes.
So maybe I announced the talk too early, but let us wait for 2 more minutes. Okay, so once again, our first speaker is Florian Luca from University of Witwatersrand, and he will speak on the transcendence criterion. So Florian, please go ahead.
Good morning or good day, everyone. I feel honored to be invited at this prestigious conference, and I am happy to see that Balu is doing so well, and he reached 70, and he's energetic and still doing mathematics. So I'll talk about the transcendence criterion. I'll start with a little anecdote. I've been visiting here at the Max Planck Institute for Software Systems in Saarbrücken, where I am now. And my host here is Joel Admin, who's mentioned in the title. And when you visit somebody, my usual style is that I try to get into their problem and see what they are working and try to be useful to them. And this seemed to have worked in most times, except when I visited Balu, for example. When I visited Balu, quite the opposite happened. He asked me to tell him about my recent work. So at that time, I had written a paper with Shankaranarayanan on square values in the sum of the first n values of the Euler function. and some other paper with Srinivas and Anirban on ordered and unordered factorizations. So we scheduled a little meeting in his office, as it was said during his felicitation around 10 o'clock, 11 o'clock. And then I explained a little bit of what we've been doing. And then he started walking around and talking to himself, scribbling something here and there. Then he sat at the table, he hand wrote 4 pages, and he gave them to me, and he said, this is the improvement. And we ended up having a few papers out of that. And that was all before lunch. So there's a continuation of that story. A different co-author joined us later, but that will be for the next meeting. So now Balu, you have the responsibility to make it for the next 10 years. So I can say the continuation of my story. So my research now is motivated by the aim to prove the following results. Suppose that B is an algebraic number of absolute value bigger than 1. Theta is real, such that this complex number e to the I theta is algebraic but not the root of 1. Then the sum of cosinus n theta divided by b to the n over those n's for which the cosinus of n theta is positive is transcendental. And these ones are my co-authors. Joel, he's from Max Planck, he's a director here. And James, we all call him Ben, he's a professor of computer science in Oxford. So where is this coming from? This is coming from a problem in electrical engineering called the LTI reachability. And the way it's formulated, you start with a source S, which is a d-dimensional vector with rational coordinates. You have a target, which is a real vector with d coordinates, and you have a transition matrix. And you have a control polyhedron that kind of tells you where to go and what to do. And the question is, decide whether there exists an n and the sequence of these controls starting from this set, it's usually a polytope, such that x sub n is in your target set, where the rule is that you start with S and at each step you multiply the previous vector by A and you add something else on this control set. And this generalizes positivity of linearly recurrent sequences, for example. And decidability is open for convex sets U. And the easiest hard instance, for example, when the source and the targets are points, and use a linear subspace, or even easier if you want. Suppose, for example, that this is not even present. Then you're just raising this matrix to the power n. And then you can ask, for example, when do I hit a certain target? If the target is, it's, let's say, a different vector, then you're asking, if you put A in Jordan canonical form, you're asking if, let's say, some power of an algebraic number is equal to some other algebraic number, and that you can test easily by looking at prime divisors and units and so on. Or you can say, well, the target is the linear subspace. Then you want that these nth powers of those roots to live in a linear subspace, and then you're asking for the zeros of a linearly recurrent sequence, and so on. And here's a couple of cases where it has been done. The challenge problem. Start with 0. The target is the set of points in the plane with the x coordinates at least c. The control polyhedron is the segment 0, 1 multiplied by the 0 vector. And the transition matrix is this one. It's like a rotation matrix, but you divide it by b because you're going to sum it along as you go along and you want to obtain a convergent sum. So what you do is that then at every step, you take the nth power of this matrix, and at every step you have to do something, shifted by one of these u's that have to live in this set and sum them up. So to maximize your chances that the answer is at least C, what you do is, well, you raise this one to power n. Of course, the first row becomes cosinus of n theta. And then you want it to be the sum to be greater or equal to C. So then you do the obvious choices. If you're positive, then you take the 0.1. And if it's negative, then you take the 0.0. So you put this cosinus of n theta or you don't put it according to whether its sign is positive or negative. And that's exactly the problem that we are looking at. And the problem becomes difficult when C, it's, let's say, a rational number or something that, let's say that the limit of this is equal to C, and C is an algebraic number. And then you compute this along, and then you're going to have a hard time deciding whether you're going to pass this threshold because you're always a little bit below that. And then you do your estimates about how fast you're going and so on. And maybe you will make it, maybe you'll stop before going there, maybe you'll pass it at some point. But if this point C is exactly the limit, then you're not going to be able to decide. So the notation, this is just some example of what we have been proving, but let's see in general. The notation is we start with a number, which is complex algebraic, absolute value bigger than 1 to make this series convergent. Theta is really rational. Take a finite union of intervals of rational endpoints in 0, 1. Actually, I changed the slides a little bit now. This A looks only like a set of rational numbers, but we are going to think of the intervals that are between these rational numbers, from 0 to R1, from R1 to R2, from R sub L minus 1 to R sub L, and from R sub L to Z to the point 1. So you have L plus 1 interval that are spanned by that. And you take some vector with coordinates in Q bar L plus 1. You don't want all of them to be 0. You take some vector with algebraic contents. And you look at the characteristic function of the points n such that n theta belongs to the ith subinterval. So if n theta is in the ith subinterval, then you pick the number ui, and you keep on going like this, and you divide by b to the n, and then you sum it up over all the n's, and you get some number. Our results say the following. Suppose that B1 up to Bk are multiplicatively independent algebraic numbers, they have modulus bigger than 1, then these amounts that I defined before are linearly independent over Q bar in one of the following 3 cases. If the absolute values are all distinct, if the number theta is quadratic, and if k is equal to 2 and theta is the ratio of 2 logs. How do we deduce the result announced in the abstract? Well, take theta to be a real number, take B algebraic with absolute value of B bigger than 1, and take theta real such that e to the I theta is algebraic but not a root of 1. And then let's try to write this number in a form that resembles what we had on the previous slide. I take the first number to be b to e to the I theta, the second number be b e to the minus I theta. I write the cosinus of n theta using its formula as e to the n I theta plus e to the minus n I theta over 2. So I split this thing into a sum that looks like that. And I recognize that it's a linear combination with rational coefficients of those 2 examples, where now, who controls when is cosinus of n theta positive or negative? You take the number theta 1, which is theta divided. So n theta, cosinus of n theta is positive or negative according to whether n theta modulo 2 pi is between 0 and 1/2, and then between 3/2 and 2. So if you scale it by 2 pi, then you get the set A of points is 1/4, 3/4. Between 0 and 1/4 and 3/4 and 1 is positive, so you take the numbers 1, and in the middle is negative, so you omit it. So these ones are, then what other deduction did we need? Conditions, we needed some conditions. For example, multiplicative independence. Well, suppose that they are multiplicatively dependent. If you raise b1 to x and it's equal to b2 to y, where x and y are integers, then you compute absolute values, d to the I theta goes away, you just get b to the x equal b to the y, so you deduce that x has to be equal to y. The absolute value of b to x equal absolute value of b to y, so you deduce that x is equal to y. Once x is equal to y, the b's go away, and you get e to the I theta times x minus y is equal to 1, but that contradicts the assumption that e to the I theta is not a root of unity. Of course, if e to the I theta is a root of unity, then these guys basically become sums of finitely many geometric progressions, and you get an algebraic number. Let's take more notation now. So before, what we did, we had this number, but we are putting the characteristic function of that interval in there. Now we are not putting the characteristic function, we are taking the integer part of n theta plus ri, where ri are the same as the numbers before. So this Sturmian sequence, if you want, this Sturmian series, which should be the sum for I equal 1 to n equal 1 to infinity of 1 over b to integer part n theta plus ri, and then we take a linear combination of that. And then we even take more numbers and assume again they are multiplicatively independent, they have modules bigger than 1, then those numbers are linearly dependent over Q bar in all these 3 cases. This has already been done before for the case k equal to 1 and b1 greater or equal to an integer, and r1 could be any real number. That's a paper of Adamczewski and Bourgeois, which appeared in Krelle in 2011. So what I will do, the plan of my talk is to set up the stage, do the little things needed to understand the statement of the subspace theorem, give a few examples, then revisit the theorem that I proved with Jan Bourgeois and Boris Adamczewski. That was done in maybe 2003, 2004, when Jan was visiting me in Morelia. And then we will see how to tweak that, that proof in order to obtain the results that I am announcing here in general, and then we will check the conditions. For a prime number p and a rational number x, we define as usual the p evaluation of x as being 2p to the minus the exponent at which p appears in the factorization of x. And then I take the set of all valuations, which is the symbol infinity and primes. At infinity, I give it the absolute value of x. And here is the product formula, which is basically a consequence of unique factorization, if you want. Because when you take the absolute value of x, you get the number itself with the primes at the correct exponents. And as you go along, the primes, the p-adic valuations pick up the primes of the negative of the exponents, and then you get 1. And in this side, this product makes sense because only finitely many of its factors are different than 1. And the way to extend it, you just take some algebraic number x, then you take some field containing it, you take the relative norm of x with respect to that field, you get a rational number, you compute the p-adic valuation as it's indicated here, and then you scale it by the degree of the field. So if you do that, if you verify that, and this definition does not depend on the number field that contains x. And for a vector, I'll take max to be the max of the coordinates. So the subspace theorem, just formulated over Q, it's well, over Q in the sense that the unknowns are all integers. I will have to go a little bit to algebraic integers and algebraic numbers later on. But for now, I take a finite set of valuations containing infinity. For every member of this finite set of the valuations, I'm going to take m linear forms in m variables, which for every s are linearly independent. And I'm going to fix a number delta bigger than 0. Then the set of points with integer coordinates, such that this double product is smaller than the max of them to some power minus delta, is contained in finitely many. Here it should be many, not many. Finitely many proper subspaces. So the p-adic valuation, I defined it for algebraic numbers, and the infinite one is just the modulus. Here is the model application. Take a finitely generated subgroup of Q star, take some algebraic coefficients, you may assume that none of them is 0, and look at this linear form, and ask of this linear form in those xi's to be small. Not very small, just a little bit smaller than what is expected, which is the absolute value of x, the maximum to 1 minus delta for some fixed delta. And you see the advantage of copy-paste is that many has propagating through different slides now.
Excuse me, Florian.
Yes.
Subspaces, you mean linear subspaces?
Yes, I mean linear subspaces. Yes, some equation with some coefficients in Q bar equal to 0. That's
Thank
what
you.
it says. Oh, I see. It should be, well, technically it is over Q bar, but usually one can prove that if you have, you can prove that you can take the coefficients to be actually over Q. And this x is a number whose coordinates are both integers and in this finitely generated subgroup. And the model application, the way it works, it's a very easy argument. You apply the subspace theorem in the following way. You take the set of finitely many primes are exactly the primes that somehow determine your multiplicative subgroup, so for which there exists an element of the multiplicative subgroup with the property that the valuation of that prime is not equal to 1. Suppose, for example, that x sub 1 is absolute value of x. And what you do, you try to apply the product formula. If you apply the product formula in here, if you take all the x's to be exactly the coordinates, then you're going to get the number 1 and you don't get anything. So you have to do a little bit better, but not by much. So then what you do, you use this equation. And you say, well, what I'm going to do, I'm going to take all the variables and I'm going to take all the linear forms corresponding to all the valuations to be exactly the coordinates, except for the largest coordinate, the infinite valuation, I'm going to take it to be that linear form which I know that it's small. So now the way it works is that in the variables where all the valuations are equal to the x's, then because of the product formula, you get 1. And in the point where you have x1, you get the saving, which is 1 over x1 from the finite valuations. But then instead of putting x1 back from the infinite norm, you just put x1 to the 1 minus delta, and you already saved. So this is all there is. And the most fascinating applications of the subspace theorem are just variations of this one idea. Let's see, for example, this idea can be used to prove the fact that an S-unit equation has only finitely many solutions which are non-degenerate. And you just change the form on the left by a form at some prime p, basically. Now, model application 2. Now, suppose that you have the same problem, except that now one of your variables is no longer an S-unit, but that all the other ones are. And you still want to deduce the same conclusion. So Z is an integer. The other guys are integers which are from the finitely generated multiplicative subgroup. And I want to apply this. Well, I applied in the same way. What is the difference between this one and the previous one? In the previous one, I had a much smaller saving, which was x to the 1 minus delta, but I knew that x1 was an integer. Now I don't know that z, I knew that x1 was in the subgroup gamma. Now z is not in the subgroup gamma, so there is no way to save from him with the finitely many primes. There is nothing coming into the denominator. So what I'm doing, I'm just taking again the forms corresponding to all the finitely many places are going to be the variables, except for the infinite place where I'm replacing the form corresponding to z by this small one. And notice that z is bounded by the absolute value of x, because this is small, therefore the absolute value of z is at most up to a constant, which is the sum of all these coefficients, the absolute value of x. Now you want to allow rational numbers. Well, when you allow rational numbers, it becomes a little bit more complicated. Now you have to allow rational numbers, but they have a certain structure. For example, I can take rational numbers to be in a multiplicative subgroup, but I would want those rational numbers to control, in some sense, I want the rational number itself to not be smaller than its numerator or its denominator, not smaller by a significant amount. Let's say I want them to have roughly about the same number of digits or to be of the same order of magnitude. So this I can interpret by saying that if I take the logarithm of the rational number and I divide it by the logarithm of the numerator of the rational number, then this ratio stays away from 0. And now I'm looking at the same thing, but now those guys are rational numbers. These guys are rational numbers with this structure. And z is an honest integer. And I want this inequality to hold. And the conclusion is that if all this is true, then again, the solutions are infinitely many proper subspaces. And now let's see the way it works is what you do, you go to the integer world. So you put y to be the least common multiple of all the denominators. Then, of course, these numbers are bigger than 1. Xi is bigger than 1. I forgot to say that. This xi should be bigger than 1. Therefore, the y's are at most the x's. So y is at most the max of xi to the power m. And the max of xi to the power m somehow is controlled by the maximum of the rational numbers themselves, which are in there. So I can control that with that. And then I can multiply across by the denominator. And these ones are integers now, these ones are S units. So this, by the product formula, the product over all the valuations corresponding to these coordinates are equal to 1. In that coordinate, I keep the finitely many places, so I'm saving my y back in here. And then z, I don't put it. I just replace the infinite form by that. And this is what I get. So it also works in this case, but it needs this extra assumption, which actually is satisfied in some cases. The most natural case in which it is satisfied is if you work with powers of the same rational number, which is bigger than 1. Then, of course, for that rational number, you write it as a ratio between two integers. You find the eta, and that eta is being preserved as you work with powers of that. And if you have finitely many rational numbers, let's say k of them, then you pick an eta that works for all. And if you live inside the monoid generated by them, by monoid, I mean not the subgroup, you're allowed to multiply but not divide. So take product of those guys to non-negative integer powers, then this condition will hold. And there's variants of it. For example, suppose that you want to allow z to be a rational number. Of course, if you want to allow z to be a rational number, then again, the absolute value of z should somehow control the denominator of z. And once you do that, then this denominator of z in here, you have to lift it, and it's going to come up here, and it's also going to propagate into all those guys. So when you go to compute your double product, then this denominator of z is going to come into here to some power, which is going to be, well, at least m or something like that. So if this inequality is true, so the absolute value of z somehow controls the absolute value of the denominator of z, then of course the absolute value of z was smaller than the absolute value of x, so the absolute value of x controls that as well, and so on. Now there are formulations which I didn't formulate, but you can do it for algebraic numbers. If you do it for algebraic numbers, then you have additional complications. The additional complications come from other infinite places. In rational numbers, you just have one infinite place. You can extend that somehow to the field of all algebraic numbers. But at the end of it, although your form has algebraic coefficients, your unknowns live inside the rational. If your unknowns now will live inside some finitely generated some number field, then you have to allow the valuations, the infinite valuations corresponding to that number field. So now you need to control this kind of inequality. So you need the absolute value of xi, let's say just the one corresponding to that infinite place where you just extended it. You wanted to somehow control the absolute values of the numerators and denominators of all the conjugates of these things. And again, it looks like a strange condition, but it works if you work inside, if you have B1, B2, Bk, some algebraic numbers of modulus bigger than 1, and you work inside the monoid generated by those powers of them with non-negative exponents, then everything works. And if you have, and of course, inside here, there is other things, there is other infinite places that come in and they sit on the top and you have to win against them. But if delta is big enough, then you win. So this is all you need. So this was basically, I broke it up into several steps of difficulty, how you would go in order to start with some nice clean result about an application of the subspace theorem if you work with integers whose prime factors live in a finitely generated subgroup, whose prime factors are all in some finite set, and go all the way to algebraic numbers with certain property. Now let's review the result that I was mentioning in the title. The result that I was mentioning in the title is the following. Take an integer b greater or equal to 2. It must be an integer. Take a sequence with values in 0, 1 up to b minus 1, which is not eventually periodic. So it really looks at base b expansions of numbers. So these ones are digits. And now suppose that this pattern of digits has the following three properties. There exists some parameter w, such that, and two sequences of words, UN and VN on that alphabet, such that for every N in that sequence, this expression looks like it has a prefix of length Rn, and then it repeats with length Vn, but it doesn't repeat enough many times. It repeats a little bit. It repeats, let's say, once and then a little bit more, where this W, if it's not an integer, you have to take the integer part of it or something like that. Then you also know that the sequence of ratio length, so between UN and Vn, is bounded, and the sequence Vn tends to infinity. So assume these three conditions are met, then this number is not rational. It's not algebraic. Comments. How important is it that the set of values of A is really in this set? Can we take some other set? Can we take some finite set? Can this be any finite set of complex numbers? How about a finite set of algebraic numbers? How about the condition that B is an integer? Can I make it a rational number? Can one replace this by the weaker condition that B is algebraic? And this is the goal of our paper. And let's visit the proof of that formula. The proof of that formula, what it does, it takes the number that you have, and then it takes that guy that's trying to approximate the number that you already have, and supposes that this pattern continues indefinitely. So in this way, it creates this rational number. And then the point is that the difference between these two rational numbers coincide at the first cardinality of UN plus cardinality of Vn times omega times. So they coincide in the beginning and a little bit. Let's put Rn and Sn for these cardinalities. So this is a spelled out version of that. And then this guy has some compact formula. And as I said, this number and that number, they coincide of the first. Now with this notation is Rn plus Wsn location. So you take the difference between them and you get this one. And this one, actually, it's an honest inequality. It's not even a big O sign, just because you're working with numbers up to B minus 1. So what you do, you multiply this across with you replace this guy by that guy, and you multiply across, and here is what you get. And this is the model application part 2. Why is that? Here you have a number, which is an S number. Everything's an integer. Here you have another S number, and here you have a number you don't know, but it's an integer. And you have a tiny saving, so you apply the subspace theorem. But the subspace theorem is not magic. It only tells you that these guys have to live in a subspace, and you still have some work to do about saying what's what with this subspace. Well, so we visit the proof. This condition 2 controls the height of that number. Yes, maybe I forgot to emphasize that. The fact that the Rn over Sn is bounded, it basically means that this number B to the Sn is up to some coefficient delta, which encodes the ratio of Rn to Sn. It controls the maximum of the numbers in that formula. So I apply the subspace theorem, and I get to that infinite many of those n's must have the property that these 3 parameters are on a linear equation. But now the great thing about that is, who is the linear equation? If you have just 2 forms, a linear equation is just a number. If you have 2 variables, a linear equation x plus by equal to 0 means x over y equal minus b over a. But here you have 3 of them. But the point is that here you already have a candidate for a small linear form. Is that one? That one is already small. So then how can a different one be equal to 0 if this one is already small? Since that one is already small and there must exist one which is equal to 0, then that one has to be the 0 form. But now that that one is the 0 form, this means basically that this number, the difference between the number and its approximant, is not only small, it's actually equal to 0. But if it is equal to 0, this means that the tail has to vanish. But how can the tail vanish? Because the tail has basically positive coefficients if it is there. Well, now one has to invoke the fact that SB of A is in fact the base B expression of this number. So if you look at this proof, then you realize that this proof is somehow a combination between an invenciones annals of mathematics type paper, which is the subspace theorem, and an elementary criterion that one learns in school namely that, that the base B expansion of a number is unique. So, and somehow that was great. It's a great theorem and solved some important problems. But it would be good to eliminate those restrictions. So you want to make some progress. So, oh, I think I deleted one slide. Yeah, I deleted one slide for me. Okay, well, no, okay, it's over here. So in order to make progress, you want to do two things. Thing number one, you want to get more expressions like this. You want to get expressions with the property that W minus 1 is bigger. You might make some sacrifices. You might have some other terms in this side. But first of all, you want this guy to be big. And secondly, you want to remove this elementary condition and you want to replace it by something which is somehow more manageable, that allows you to do better applications. Well, Bourgeois and Adamczewski, they wrote an annals paper after that in which they allowed the number B to be a Pissot number, but that really doesn't change anything because for the Pissot numbers, the infinite valuations are all bounded, they didn't have denominators, so the same thing completely works. Just some little fiddling at the end was needed about the tail. So here, let's address I. So I'm going to retain the condition on the existence of W, but I want to ask more. Actually, I don't want W to exist and to be bigger than 1. I want every W to be good. And I want every W to be good for the same sequence. So here's what I want. I want a sequence. Sequences Rn, Sn, like they were before, with the following property that for every integer W, not only for one which is fixed and it's bigger than 1, for each one of them, there should exist infinitely many n's, such that with words un and vn in this sequence, they don't even have to be all of them. For every W, there could be a subsequence of the mother sequence, let's say, with the property that when I do what we did in that criterion, I take the number A and I take this approximant, and I take something, I don't know why it occurred to me to write it like this, for a symmetric difference. What a symmetric difference of these two words is, it encodes the locations in which they are different. So I don't want them to be identical, but I want them to be different in places that I can control and that have a certain structure. And here is the structure of that place. The place of differences should be basically a union of arithmetical progression, starting all of them at the same ratio, Sn, which start at a certain number of spots. So there are some spots here. So once you start, you keep on adding multiple of Sn and you sit inside that set. And this is one. And secondly, the number of seeds, so where you start those progressions, should be bounded in terms of W, but independently on n. So what can vary here with n? So what is bounded? Given W, the number of seeds is bounded. Once the number of seeds is bounded, the number of all elements is bounded, because for every seed you add at most Sn once, twice, up to W times. So if you have a bound on the number of seeds, then you have a bound on the cardinality of that. It's bounded by W. The only thing that's variable is that for every n, those numbers are going to be different numbers, just because this interval shifts around with n. But I want the numbers, the cardinality of them. And in addition to these arithmetic progressions, I want my sequence to be constant on that arithmetic progression. So the sequence that I started with, I want it to be constant in that arithmetic progression starting at that seed. Additionally, actually, I don't need it that complicated, but I only need, let's say, that the difference between any two consecutive guys from here, maybe adding Sn and so on, tends to infinity. But I can formulate it like this. For every finite set of rational numbers, if I consider linear combinations between the indices in this interval with coefficients in this finite set, then these linear combinations should either be identical 0 or go to infinity with n. I don't want them to every now and then be bounded by something. And I'm retaining those conditions about the ratio between Rn and Sn and so on. But in our applications, it is always the case that Rn is equal to Sn. All right, so let's put this condition to work. So we go back and we follow the method. I take W, arbitrarily large but fixed. Now I can assume that it is large and I have this choice and I look at that. Now, because of this interesting set of conditions, I do have a difference as I go from here to here. But the point is that those differences are arranged in that way. And on those differences, the initial sequence is constant on those differences. And the approximate sequence is also constant in those locations. So if I take the difference between them, there's a constant, which is the value that I see in A minus the value that I see in B. And because of that, I get these coefficients, which are fixed. And then I have an approximation like this. And these L's, they run through the sets of the seeds where the difference start, and then is b to the power Sn minus 1, and alpha n is being retained. Alpha n is the same as it was in the ABL theory. It had the structure b to the power Rn multiplied by b to the power Sn minus 1. But look at this b to the power Sn minus 1. It's beautiful. Now I can multiply it up. These C's are, of course, they come from some fixed rational number, from some fixed, I'm going to address later whether they can be rational numbers or integers. And then this G sub n is big O of W. This is important. It's important that the number of terms here is bounded in terms of W. So I multiply everything across and I get this. So this looks exactly like ABL. I have a mistake in here. Here should be Rn plus Sn. So in ABL, this term wasn't there. And W minus 1 was positive. Now this term is there. Because this term is there, now I can do basically whatever I want. I can, the left-hand side is a linear form in J plus 3 indeterminates. And assuming alpha is algebraic, it has algebraic coefficients. And now the idea is that these guys are S units. They are S units, so even as algebraic numbers, they are S. As algebraic integers, they are S. If, let's start with algebraic integers. If I put algebraic integers, then I take, let's start with integers first. Then these guys are S units, they go away, and it's the same proof as it was before. But now since this W minus 1 are forced to be whatever it wants, then what I can do, I can start lifting up. Denominators in here, they don't matter what they are. But because they simplify, because they are S units. Denominators in here that come with a Pn, the point was that Pn is the sum of powers of B up to length Rn. So even if the denominator of Rn, it comes, of course, it's going to be an S unit, so I'm simplifying it, but it blows up this guy. And then, of course, if I have algebraic numbers, then I have to consider other infinite valuations and so on. So all these things are going to pile up on the right-hand side when you compute the double product. But all those things, these guys don't matter because they are S units. They will only come from these guys. And this guy over here, it's basically of the size something to the power Rn plus Sn. So even if you take conjugates of that and you multiply with denominators and so on, you're going to get an amount to the power Rn plus Sn, which is an amount to a bounded multiple of Sn. So once W minus 1 exceeds that bounded multiple, then you win. And once you win, then you write down some conclusion of the subspace theorem. And the conclusion is that there should be finite many subspaces. Now we go back to the proof of that theorem and we say which ones are the subspaces. When you go over here, of course, I have a linear form which is 0. That should be the subspace. Well, does it work? Well, suppose that it's not that one. Suppose that it's a different one. So I have a small form and I have a form that is 0. So I'm going to do what I did in school. If I have two small guys, then I'm going to take a linear combination of them and it's still a small guy. So I take the form that is 0 and I subtract it out of the small form with a certain coefficient so that it knocks off one of the variables. And then I go back to my problem. This side hasn't changed because L1 was 0. Now my problem has fewer variables and that form is still small. So I apply the subspace theorem to it and I keep on going down. By the time I get down, I get to just one indeterminate. Which indeterminate can that be? A power of B that is false, or it could be this Pn that was coming from my number. But you see this Pn, as I said, it has size roughly exponential to Rn plus Sn. It might have denominators and conjugates and so on, but again, this W minus 1 can be taken as large as I want. So if W minus 1 is large, then the norm of this guy becomes 0, therefore this guy is the 0 guy. But this guy was tending to alpha, so alpha is the 0 guy. And since alpha is the 0 guy, all these three guys are not there. And then I have this one. And now this form should have the property that somehow should be the 0 form. But this is an S unit equation. if you make this one. And in S-unit equation, for example, if I have this condition that the differences between those seeds and so on tends to infinity, then this S-unit equation also can only catch finitely many of those guys. So because of that, everything works. And therefore, I conclude not only that the subspace theorem gives me that there is a zero form, but that the subspace theorem tells me that the zero form is this form. It's exactly like in the ABL theorem. This means that the tail is zero. But now we have to look at the tail. We cannot invoke some elementary criterion. We have to look what's happening in the tail. Well, what's happening in the tail? Remember, I started with my number and I eliminate some approximation. Now in the tail, the number still remains there. And then there is these perturbations that come from that, those approximations, which are indices that are congruent to I1, I2, In, where these ones have some constant value that was coming from the approximate, and these ones have the values that they have. So the question is, can this happen infinitely often? Well, here's one way in which we dealt with it. Suppose that you take the first two values of your sequence, which exceed Rn plus Wsn, which are incongruent to each other or to one of these guys modulo Sn, such that that digit was not the digit it was supposed to be. And the reason that these always exist is exactly the non-periodicity, because I stopped at some W. Once I stopped at some W and some N, the problem lives in some finite world. So if this doesn't exist, it just means that the sequence will be eventually periodic. So for every single N, and for that big W fixed, these two guys must exist. And I'm assuming that K2 of N minus K1 of N is unbounded as I run over the N's with this problem. Then if this relation is true, then what I do, I separate the first guy, which is K1, and the one with K2, I put it back on the other side, and then I scale, so I get that this difference, which is not zero, is smaller than 1 over absolute value of b to the K2 minus K1, and that is false if K2 minus K1 is unbounded. This is the theorem now. Suppose that A satisfies I prime 2, 3, and 4, then for every algebraic B with absolute value bigger than 1, the number S sub B of A is transcendental. Well, believe it or not, this machine works in general. So we can start with algebraic numbers B1, Bk, which are multiplicatively independent. I would like to know that those numbers are linearly independent over Q. I set up the same machine. I suppose that they are linearly independent, that's a minimal relation, so there is no independence for K minus 1, although that is not needed. And then what I do, I write those estimates now. So it's the same things. These guys are the same. These D's are the lambdas multiplied with the U's. And these are finitely many. Everything lives in some finite field. Okay, right. So I get this guy over here. And then I enlarge the field such that it contains scalars and so on. But look at this guy. These guys are the same indeterminates, are b to the power t Sn minus 1. But of course, now there are k of them, and I have to multiply across. So when I multiply across, I get this scary looking guy in here. The scary looking guy somehow is bounded in terms of the number and in terms of the number j. So there is this j here, which was the set of seeds where things were changing, but that j is bounded. I can assume that it is fixed. And here, this C3 is, it's going to be a huge constant because it comes from all those guys. And in addition to that, you have to take the other infinite valuations. So this gives you things which are even more bad. But the point is, as I said, and I stress out again, these infinite valuations depend only on the variables at the beginning, not on the variables at the end, in that because, those guys are S units. And of course, there is these variables. So now I have a bunch of unknown guys, and they are all going to pile up in here. But also these guys are controlled and their valuations and so on, basically by the minimum of the absolute values of all these guys. So this one is my subspace theorem. I apply the subspace theorem. I get there finitely many subspaces, and then I have to go inside the subspace. And the same conclusion is being retained. Once I go inside the subspace, that this is exactly the formula that it has to be. And the point is, again, the same thing. You keep on reducing it. If it's not that formula, it's a different one. Until you get to things of the sort, let's say an unknown contained this one. Well, since this one is so small, you can say that this unknown must be 0, therefore that limit doesn't exist. So now I can use the induction hypothesis that the first k minus 1 of them were linearly independent. Or what other unknowns can be? They can be unknowns that come, let's say, from the B's, but that's an honest S-unit equation. And when you have S-unit equation, the fact that the B's are multiplicatively independent, first of all, they tells you that if you have an S-unit equation that has infinitely many such solutions, which are primitive in some sense, then they should come from a single B, and the way these exponents are conspiring in there. But those exponents are spaced out, so that can't happen. So because of that, you just get the same structure. Then you look at the tail. Now the tail is just the sum of the previous tails. This K2 and K1 are the same. Then you just have some coefficients in here. And then you want to do the same thing. You want to divide by that. But who should you divide by? Because now you have a bunch of guys. For example, in the case they are all distinct, then this is impossible. Because what I'm going to do, I'm going to separate the minimal one. The other ones, they really don't matter. I'm going to throw them away. And I'm going to separate the minimal one. And since the absolute values are all distinct with the minimal one, it's already doing the job. Then what else can you do? You can say, oh, okay, let me use a known consequence of the subspace theorem, namely that if I take a linearly recurrent sequence, then this one cannot be very small. It can be small, but only by, let's say, an amount of epsilon. So this means that if I take this guy, then it's bigger than 1 over the minimal of them to the power 1 plus epsilon times k1 of n. And I can make my epsilon as small as you want. Well, if you do that in this sign, then this becomes 1 over b to the 1 plus epsilon k1, and this becomes k2. And therefore, it should be that k2 is smaller than 1 plus epsilon times k1 of n. So if you are in an instance for which you can prove that this is not true, namely, you can prove that k2 of n over k1 of n over these two minimal indices, the inf of that is bigger than something that's strictly bigger than 1, then you win. And it turns out that you actually win when theta is quadratic in that way. And assume next that k is equal to 2. In this case, I divide by lambda 1. I can use linear forms in logs. And this side is at least 1 over k1 of n to a constant. And then I interpret these two guys. And then I get k2 minus k1. So if k2 minus k1 tends to infinity, that's fine. But if I can prove that it tends to infinity faster than the log of the maximum between them, then again, I'm done. And that actually works with linear forms in logarithms. You can prove that in the case when k was equal to 2 and theta was the ratio of 2 logs, these numbers from here actually are bigger than a small power of the k2. So this
Sorry, Florian, to interrupt you.
Yes.
How more time do you need?
2 more minutes.
2
I'm
more
almost
minutes.
done.
Okay.
So these ones are the conclusions that I need. And now let's go to our structure in which this thing was given by the fractionary parts of n theta. Then you have to interpret what this set means, this set of differences. This set of differences, there's the u's that are below the denominator of some conversion to theta, such that if I shift u by a multiple of k and of a controlled amount up to w, I land in an interval. But if I shift u with qn by a different multiple in the same interval, I land in a different interval. And these intervals have to be consecutive. So basically, if I write here, it's important that these ri's are rational. I write them as rational numbers, pi over q. I multiply q across. And then I get that these numbers L, U, have the property that there exists some L up to W, such that the distance between this multiple of theta to the nearest integer, which should be congruent to pi modulo q, should be small. And here is the answer comes in two flavors. And let's say that the partial quotients are these ones. If Bn is unbounded, then for infinitely many Bn's, this set consists of numbers of the form delta Qn, and delta belongs to a finite set. In fact, the numerators of these numbers divide Q, and the denominators and the numerators are at most Q times W. And if Bn is bounded, then this consists of numbers of this form, where delta 1 and delta 2 belong to a finite set of positive rational numbers of bounded height. And now everything works out. then this condition is also satisfied because at each step you add really tiny amounts. So once you've changed once, then you don't change all the way to W. And then, for example, this condition follows because this is quadratic. When you have a quadratic number, and you look at guys like this, these guys like this, the QNs live in finitely many linearly recurrent sequence, which are driven by a characteristic equation where the roots are the fundamental unit and its conjugate. And if it's something that I learned about these things, is that if you have finitely many sequences like this, and then you arrange terms between them, which one is bigger than which one, then if you divide those nearby terms and you tend to infinity, what you get the quotient between the constants that are in the Binet formula. And this cannot be equal to 1 because these guys are quadratic numbers. If it's equal to 1, its conjugate is equal to 1, and the sequences were the same. So it has to be bigger than 1. So this verifies the condition with quadratic. And for the last one, you use Erdős-Turan-Koch-Ma, because you have to use something about the discrepancy when you fish around for this K1 and K2. You have to say, oh, I put them in this interval, and this interval contains more shifts than it was containing. Therefore, this is how I find K1 and K2, and I get the conclusion. And with the Sturmian sequence, is really the same. You just have to reinterpret it. And that's it. Many more birthdays and theorems, Balu. Thank you.
Okay, thank you. Thank you, Florian. Any questions, please? Okay. Yeah.
Yeah, I had one question. Your W is changing, is it? As opposed to the previous theorem. For every W, you want a sequence.
I don't hear you well.
I also didn't hear well.
It's breaking. The voice is breaking.
Can you hear me now?
Yeah.
No, Florian, if I understand correctly, the difference, the previous criteria of yours is that your W is changing now, is it? For every W, you want a sequence, is it?
No. I have the same sequence. You see, the sequence is the sequence of convergence.
No. For every W, there is a sequence for this office. I didn't understand.
No. There's a sequence such that for every W, when I look inside, for infinitely many n's in that sequence, when I look in that table, I have that structure. But the sequence is the same. The sequence doesn't change. The sequence is the sequence of denominators of the continued fraction for theta in that concrete application. It's just the W. It's like, imagine that you walk on some mountain and then, like in the ABL theorem, then you get to some point and you have a W bigger than 1 for which it works, but then you get to some point for which it doesn't work, and then you give up. Okay? You shouldn't give up. You should go ahead. And as you go ahead, you say, oh, wait, listen, there's a little change in here, but it's not that bad. It changes in this way. Oh, and there's another change in there, and so on. So with these Qs, the way I can go with larger and larger Ws. Of course, if Qs is small, then at some point for some large W is going to break down. So then if you have a W that's large, you have to start with a much bigger Q. But this is the whole idea, basically.
Okay, more questions? Okay, looks there are no more questions. So let us thank the speaker.
Thank you.
And we'll start in 6 minutes. Kalyan, let us maybe try if it works.
Yeah, so let me try. Thanks. Share screen.
They make you co-host?
No, I think
I'll make it now. Anyway, he can share.
Is it okay?
Yeah. Okay. Yes. Yes, I think it's okay. Yes.
Yeah, but
Yeah, I could not locate him earlier. Okay, now I can see.
yeah.
Okay. Okay. So let us continue. Our next speaker is Kalyan Chakraborty from the Harish Chandra Institute and Kerala School of Mathematics. And he will speak on the Fourier coefficients of set and Hilbert modular forms. So please.
Yeah, thank you, Professor Balu, for introducing me. And so let me begin by wishing Professor Balasubramanian a happy birthday, even though it's a couple of days late, but still, it's a privilege to be here and celebrating this elite conference that the organizers have put in front of us, and almost all the number theorists as I see, are here. So it's really a true tribute to Professor Balu, and I am one of those privileged ones who I know got the company, got the suggestions, guidance. Professor Balu was always there for all of us. The number theory school that I see